Hello folks. Our problem today is to think about how we can get at the idea of the center of a data set, and from there think about spread and forming intervals that capture important aspects of the data. Very basic descriptive statistical kind of idea. So let's start with this context of 20 total rainfalls through the month of March in the Blue Ridge Mountains, sampled across the last 1,000 years. To aid us to visualize, instead of just putting the points, their inches, on the x-axis, I've lifted each of these points up some random distance just so that they don't overlap and block each other, so that we can see each one. So the height doesn't mean anything, it just allows us to see all the data points. Remember, it's the x values that are the inches. It represents some month where it rained that many inches. Like here we've got a month that rained over 14 inches. Okay, so let's get to it. So maybe the first thing I would do with this is throw one of our visualizing tools, be it a histogram, or since it's numerical data, a histogram, or a Botson-Whisker plot. And both of those can help us lead us to some solution to what a center is. But when I do this one, and it's just a basic one, starting at 0 and I go bend widths of 2 inches, I see that there's a zone here, these two especially, that has a lot of the data. The data density is the greatest in here, and it peaks right here. So I might say for this that 7 makes a good, and when we talk about peaks we use the word mode, that the mode here is around 7 inches. So it's a time around 7 inches where a lot of monthly rainfalls dropped around that period. So it's about density, or how much they're clustered together on the modes. But that's one way of approaching it. Another way of approaching it is to try to bring to bear all the last 300 years of calculus. So the idea is that we want to be able to draw some line and then think about distances. So this line is got an x value, and we want to think about on the right, for instance, how many distances are there from that. So we take each of these lengths here, and how we compute those is not particularly important, not for now. But if I add up all 1, 2, 3, 4, 5, 6, 7 of these lengths, I'd get some number. And now I can come over here and do the same thing. I'd have a lot more lengths, but a lot of them would be a lot shorter. But what I'm looking for is a bar, an x value, where the lengths from the right and the lengths from the left add up to be the same number. So that's what I've drawn here, or computed here. So when we talk about this balancing point, and that's what it is, it's a balance, and I'll explain why in a second, but it's equating distances, is the mean, and in this case it's about 6.25. So if you took the rainfalls for these data points and subtracted them all from, subtracted the mean from all of them, and then add them together, you'd get 22 inches. And over here, if from the mean you subtracted each of these values and got all these lengths and add them together, there's more of them, but they're shorter, you'd also get 22 inches. And there's a unique place where that happens, and there it is, the mean. But I want to point out that it's not just about adding up distances. Another way of looking at this is a balancing point, that if we took a board in our physics, if we took a board and we put a rock on the board, all of the same weight for each of these points. So if we put a rock there, and we put a rock there, and we put a rock there, and then we put a bunch of these rocks for each of these over here. I've made a mess of this. this board would balance out. We know on a seesaw, the further you go out on the seesaw, the more leverage you have. And so if you have a bunch of people sitting on the seesaw and it balances, it's when, if all the people are the same weight, it's when the lengths of the distances from the fulcrum are equal. So that's something else the mean gives us, is if we look at the data, we can, if we have an eye for it, look at where the whole thing as a system would balance. But you can see that the balance point is not necessarily the middle point, the point where half of the data is on one side and half the data is on another side, where we're doing counts. In this case, we got 60, almost 2/3 of the data point are over on the left of the mean. Now, just before we go any further, I want to point out that it shouldn't be too stunning that the spread that we use to build up ideas of intervals in using the mean, something called the standard deviation, it also involves quantities that are like distances. And it shouldn't be too shocking that since it involves distances, the standard deviation will be affected by these stretchings, these skews. But that's something Dr. Taylor will talk to you about. Okay, so now let's look at another idea of center, and that is this counting of the data points and less of where they're landing relative to each other and the distances they are from each other, but instead just how many are in what areas. So here we know from this that right here the median is a 50th percentile, meaning if you're moving this way, 50% of the data points occur. I think I have it where we can count this. So let's see. We got 1, 2, 3, 4, 5, 6, 7, 8. This one's 9. This one is 10. And I think this one down here is 11. So I think without any way, it should be right in here. Right? Because if we count these others, they're either close or far away, 10 on the other side. So let's take a look. And sure enough. So that's the median. That's what we call the median. And it's about splitting it, being a center where it's the same number of data points on each side. So here our proportions are 50% on each side, but notice the total distances now is 18 on the left side, but 24 on the right side. So if you were to try to balance this thing would tip over to the right. Okay? So a median is not about balance. Now, if we were talking about forming intervals using the median, which we're much more capable of doing now that we have computing power, we are going to use this idea of counts and proportions to describe intervals and describe spread, because that's the most natural, since the median is about counts and proportions. Now, what I've done is I've illustrated here just on the line those 20 points, but I've gone ahead and plotted all rainfalls for every March over the last 1,000 years and made a histogram of it instead of plotting all those points. So there's a histogram of 1,000 values of rainfall, okay? But instead of using bend widths of 2, because we have enough, we can use bend widths of 1/2 inch, okay? Okay, so now what do we do? Well, let's look at one way of finding a center of this data where we can build our interval, and that is using the mean. So our mean in this set of 1,000 data is almost 5.98 inches, and the 575 data points to the left of this form the same distance of 1294.4 total distance as the 425 points to the right of this, and that's why our data has been stretched out. So we can interpret this as, well, a lot of the data, this mean would be more towards this way if it wasn't for there being some years where the rainfall was really huge, but most of the time it seems the rainfall was more back here around the 5-inch mark. Another way of finding center that we've been talking about is going ahead and saying, okay, where is the middle of the data, the 50th percentile? Where the counts are equal? So here we have 500 of the data, and here we have 500 of the data. But notice that the total distance of this data from the median is 962, about 963 inches, while on this side the total distance is almost 1600. So there's a distinct difference there. And if we were to put a fulcrum right there, a balance point, to this thing cut out of wood or something, it would tip right on over this way. And the last point, this one has a very nice clear kind of mode. It's around 3.75. And this is where the value peaks. And where the data peaks tends to be where the counts are the highest. I mean, it's where the count is the highest that we call the mode. But it's these high values that tell me that people who may, just from year to year say, what was the rainfall in March? This is probably what they'll remember is more like under 4 inches instead of these values here, because this is where most of the marches are occurring. But as you can see, this is just a little bit more than just a quarter of the values are below this mark. So even though a lot of the years were like this, it's a pretty low mark over the whole stretch of counts or distances. So just review. Let's see if we got this. So when we talk about a median, 50th percentile is a halfway place. It's where the idea of proportion and count is important. When we talk about mean, it's the classic kind of averaging of your grades where everything's added together and divided by the number. That gives you a balancing point of the data, and it takes into account skewness, and what's important is distance there. And then there's the mode, which is the place where the data peaks. Where your density is important, meaning where do the grades are all packed together are important. So I leave you with the question, as always, is if you are given a fairly well packed data, it's not all over the place, but you do have some skewing, what can you say about these 3 data points in that data set? Can you just kind of imagine a general data set and kind of understand where these 3 ideas of centers land? And remember that each one of them have a corresponding concept of spread that allows you to get at an interval of data. Okay, I hope that helps. See you in class.